Hello everybody, my name is Anya Kantrat. So today I'm here with another video of the subject maths. So the topic we're going to study today is about the stochastic matrices. So let us look into the contents. So first, let us look into the introduction to stochastic matrix. Second, what is exactly a matrix about? Thirdly, the probability distribution of a process. Fourthly, the stochastic matrices. And fifth is nothing but the example for a stochastic matrix. So, what is basically a stochastic matrix? A stochastic or a random process can be defined as a collection of random variables that is indexed by some mathematical set, meaning that each random variable of the stochastic process is uniquely associated with an element in the set. So, the set used to index the variable is called the index set. So, a stochastic process can have many outcomes due to its randomness, and a single outcome of a stochastic process is called, among the other names, a sample function or a realization. So, the stochastic process can even have either of the other names, which is nothing but due to the randomness, or you can say that due to the single output which you're going to get every time. So, it's hence called as a sample function or a realization. So basically, what do you understand by a matrix? A matrix is nothing but an ordered rectangular arrangement of numbers. The numbers can be either real or complex, or the functions which can be represented as shown in the slide. It's nothing but the matrix is enclosed with the square brackets or the closed brackets. So it includes the terms A11, A12 to A1n, followed by the second row A21, A22, so on up to the A2nth row, followed by the infinite rows you want. That is nothing but A1, M1, AM2 to the AMN rows. It can be the number of rows and columns which we wish to represent in a given problem. So what is basically a probability distribution of a process? So for any stochastic process with index set I, its probability distribution function is uniquely determined by its finite dimensional distributions. So the k-dimensional distributions function of a process is defined by f of x t1 to so on x tk. The values of x include x1 to n x, that's one x to the subscript k. It is equal to p of xt1 less than or equal to x1, so on up to xtk value less than or equal to xk value. So for any x1 to xk, it should belong to I, and the real numbers can be from x1 to xk. So the distribution function, it tells us everything we need to know about the process, which is nothing but x. So this is all about the probability distribution of a process. So let us look at the main concept, which is nothing but the stochastic matrices. So a stochastic matrix is a square matrix whose columns are probability vectors. So a probability vector is a numerical vector whose entries are real numbers between 0 and 1 and whose sum is 1. So basically it's nothing but it's a square matrix whose columns are probability vectors, and probability vector is a numerical vector which includes the real number from 0 to 1, and the sum of the numbers should be 1. So next, the stochastic matrix is nothing but a matrix describing the transitions of a Markov chain. It is also called the Markov matrix. So the right stochastic matrix is a square matrix of non-negative real numbers whose rows add up to the 1, and the left stochastic matrix of non-negative real numbers are nothing but whose columns add up to 1. So a doubly stochastic matrix is nothing but a square matrix of non-negative real numbers with each row and column adding up to 1. So when you talk about the stochastic matrix, they are of different kinds, which is nothing but the right stochastic matrix, left stochastic matrix, and a doubly stochastic matrix. So next, let us look into what is a positive stochastic matrix. It is nothing but a stochastic matrix whose entries are all positive numbers. In particular, no entry is equal to 0. For instance, the first matrix below is a positive stochastic matrix, and the second one is not a positive stochastic matrix. The example is depicted as shown in the above slide. The first matrix includes the decimal values, and the second values includes only the ones and zeros. So, instance, we can describe them each other as a positive stochastic matrix and a non-positive stochastic matrix. Next, let us look into the example of a stochastic matrix. So let us look into the first example, continuing with the red box matrix. It's nothing but A equals the given matrix. It includes 0.3, 0.4, 0.5, 0.3, 0.4, 0.3, and 0.4, 0.2, and 0.2 in the third of the first column. So basically, it is nothing but a positive stochastic matrix. The fact that the column sum to 1 says that all the movies rented from a particular kiosk must be returned to some other kiosks. So in brackets, the hint is given as every customer returns their movie the next day. For instance, the first column says of the movies rented from the kiosk 1, 30% will be returned to the kiosk 1. Second, the 30% will be returned to the kiosk 2. And the 40% will be returned to the kiosk 3. So now, the sum is 100% as all the movies are returned to one of the 3 kiosks. So a matrix A represents the change of state from one day to the next. So xt plus 1, second row represents yt plus 1 in the given matrix. And the third represents zt plus 1. It's equal to A into the matrices xt, yt, zt, which is equal to the above matrix multiplied. It's nothing but 0.3 xt plus 0.4 yt plus 0.5 zt. The below matrix includes 0.3 x1 plus 0.4 yt plus 0.3 zt. And the third row includes 0.4 xt plus 0.2 yt plus 0.2 zt. Now, if we sum the entries of Vt plus 1, we obtain the above equation, which is mentioned as 0.3 xt plus 0.4 yt plus 0.5 zt plus 0.3 xt plus 0.5 yt plus 0.3 zt plus the last row, which is nothing but 0.4 xt plus 0.2 yt plus 0.2 zt. It gives a summation of 0.3 plus 0.3 plus 0.4 to the multiplication of xt variable plus 0.4 plus 0.4 plus 0.2 yt plus 0.5 plus 0.3 plus 0.2 zt, which is equal to xt plus yt plus zt, which is the above value we have required. So thank you for watching the video. Please do like, share, and subscribe. Thank you.